combine Koopman operator theory with quantum mechanics to perform closure of partial differential equations or more general dynamical systems. This is done in collaboration with David Freeman, who's a PhD student at Dartmouth, Joanna Slawinska, also from Dartmouth, and Chris Vales, who's a postdoc, again, at Dartmouth. So there's a motivation. I don't think this is advancing the slides. Doesn't seem to.
Okay, let's click on the slide.
Oh.
I clicked. Okay, you can go forward. You want to touch none?
No, they're doing it. Yeah. Okay, so should I then be saying next slide? Okay. Okay, now it works. Okay, thank you. Okay, so the problem that we're studying is a closure of dynamical system. This is encountered in many different applications where you have a high-dimensional dynamical system that either because we do not have sufficient computational resources or simply because the exact equations of motions are unknown, we want to create an effective dynamical system that represents some degrees of freedom of the original system. I will call them unresolved degrees of freedom, denoted here by Y, by a different model that evolves in its own state space. And this has applications in many domains like fluid mechanics, climate science, molecular dynamics, many fields. And over the years, one class of closure method that has gained attention are based on stochastic closures, where basically one is using a stochastic surrogate model for the unresolved degrees of freedom. And so in this paper by Tim Palmer from 2001, basically he observed that if one is interested in doing a closure of a chaotic dynamical system, he took the Lorentz 63 system, a stochastic closure is able to recover some aspects of chaotic dynamics more effectively than deterministic closures. And in this particular case, Palmer attributed this to basically the fact that in low enough dimensions, you cannot have chaos. It's like the Poincaré-Bendixson theorem. So if one attempts to do a deterministic closure that reduces the dimension of the Lorentz 63 system to 2 dimensions, you cannot have chaotic dynamics there, but we can understand stochastic closure as effectively doing a very large dimensional augmentation of our original system by including the event space of the stochastic process. This is similar to one of the sequence spaces that Igor mentioned in his talk, and that effectively allows us to capture some aspects of the Lorentz attractor. So in this work, what we are going to be doing is to have a similar viewpoint, but instead of using a classical stochastic system to create our surrogate of the unresolved dynamics, we're going to use quantum mechanics, like using a quantum mechanical system. And this, what I'm hoping to convey is that this provides a natural bridge with a Koopman operator and transfer operator methods, since quantum mechanics is fundamentally a operator theory. So I'm not sure to what extent people are familiar with quantum mechanics here in the audience. Maybe we can have a quick show of hands if there's some familiarity. So I will go through very quickly a rundown of the basic axioms. And in a nutshell, in my opinion, a useful way of thinking of quantum mechanics from an operational point of view is like a generalization or a version of classical statistical theory, where many objects that are represented classically as functions, they become operators in the quantum formalism. So starting from the state of a quantum system, Whereas classically, if you're talking about statistical descriptions of a system, you would use probability densities. In quantum mechanics, these are replaced by so-called density operators. So, and these are operators that are acting on a Hilbert space, which depends on the system at hand. And they're positive operators of trace class and having unit trace. And you can think of this in analogy with the fact that a probability density is a positive function. It's integrable, so this is the analog of trace class, and it integrates to 1, and this is the analog of having unit trace. So we can use this as some operator versions of probability densities. Observables, in quantum mechanics are also operators. You can think of them in this case in analogy with random variables in classical, real-valued random variables. In quantum mechanics, you have self-adjoint operators as the observables. And there is a prescription that gives us the probabilities, expectation values of quantum observables given by this trace formula that is very much analogous to when you compute the expected value of a classical random variable, you integrate against a probability density. Here, the analog is taking the trace of the quantum observable times the density operator that characterizes the system. And there is also a prescription for computing probabilities of events. So here, omega denotes an event. It could be, for instance, an interval, say that we have a detector of finite resolution, and we are interested in finding the probability that we make a measurement, and we have a result that falls in that interval. That basically uses spectral resolution of self-adjoint operators. The evolution in quantum mechanics takes place by means of unitary operators, and this is where the connection with Koopman theory happens. And this is very much in analogy. So if you have a unitary operator, it acts on density, on the Hilbert space, it acts on density operators by conjugation. So this formula, you can think of this analogously to how the transfer operator acts in the classical case that pushes forward probability densities to probability densities. And finally, we're going to need that as well. There is also an analog of Bayes rule in quantum theory that you can condition, whereby you can condition a quantum state by so-called quantum effects. So these are quantum analogs of event. Again, you can think of it in classical statistics. Basically, they're positive operators that are between the zero operator and the identity operator. Think of this in analogy with how you can represent events in classical statistics by characteristic functions. So a characteristic function is a function which between the zero function and the function equal everywhere to 1. And you can condition your classical state using Bayes rule by basically when you have observed an event by multiplying your probability density by the characteristic function indexing the event and normalizing. So this is what is done here, modulo the fact that because we are in a non-commutative space of operators, we have to do this multiplication from both sides, and we have to take a square root. So this may not look superficially like Bayes rule, but it is analogous to that. So this is going to be our set of axioms, and now we want to embed dynamical systems into this framework. So, like, I guess in the spirit of the workshop, this is a very much, I think, an open-ended question. There's many interesting, mathematical and methodological questions related to that. So what I'm going to present here is like a canonical way of doing that that is related to the so-called Koopman von Neumann representation of probability densities, in case you're familiar with that. But so the idea here is that we have a classical level description of our system. I'm going to be thinking about systems that are measure preserving, and we have classical probability densities in L1, so probability density functions, and they evolve classically under the transfer operator. And as observables, a natural choice is in this case to take bounded or L infinity observables, which happen to form an algebra in the sense that we can multiply bounded functions, and they remain as bounded bounded functions. These are going to be our observables. And we have the Koopman operator, which acts as a unitary on L2. And this is going to define for us a quantum system. So for a quantum system, we need a Hilbert space. In this case, the natural choice would be L2. And our unitary that carries the dynamical evolution is the Koopman operator. This is basically, essentially, going back to Koopman's 1931 paper. Given that, we can create an embedding of our classical statistical evolution into this quantum evolution. So Q of H here denotes the space of quantum states on our Hilbert space that takes basically probability densities and maps them into density operators that are rank 1 operators that project onto the square root of the density. So the square root of the density, you can think of it quantum mechanically as a wave function, if you're familiar with that. And the important point is that the entire procedure is consistent with a classical statistical evolution. In other words, you can either, you have effectively a copy of your original system into a quantum system where the statistical behavior is consistently reproduced. Okay, and so this is all done in like an infinite dimensional setting. So this quantum system that one obtains is typically infinite dimensional. So in practice, what we want to do, we want to take that system and then project it onto a finite dimensional quantum system that is associated with finite rank operators. And again, there are many ways this can be done. And there are many interesting, I think, open questions related to this. But effectively, we're building a family of projected quantum systems that evolve in a finite dimensional subspace of our Hilbert space. Now, the one, I guess, take-home message that I want to convey from this talk is that basically doing this kind of projections allows us to preserve structures of the original system that would not have been at least immediately possible to do if we were working classically. In other words, by putting first our system into this space of operators and then projecting, rather than projecting first and then potentially embedding it into a system of operators, we are able to preserve positivity, which is important in many applications. For instance, in data simulation or closure, when you're dealing with physical systems, you want to, for instance, if you have quantities like energy or temperature and so on, you want to preserve their positivity. And it's very natural to preserve positivity of operators by composing them with projections. But on the other hand, orthogonal projections of functions do not preserve positivity. You have like Gibbs phenomena and so forth. So that's one take-home message. And how much time do I have? Excuse me. Okay. So we have basically this finite dimensional projected quantum system that gives us some approximation of our original classical system. Now we want to go back and use that in the context of closure. So for that, what we're going to do is we're going to take as our surrogate state space that is basically up to the choice of the designer of the method. We're going to use the space of quantum states over our Hilbert space. L2, we're going to be working in this setting of measure, preserving dynamics. And the fluxes, these are the closure terms that we need to provide in order to have a closed evolution. Here, we're going to represent them as quantum observables, in particular multiplication operators. We are going to describe the state of the unresolved degrees of freedom by a quantum state. This is how we're going to model it. And we're going to have a coupled evolution between a classical and quantum system, which I'll explain in more detail in a moment. I'll just mention here very briefly that there is a data-driven procedure to implement this scheme. I don't have time to go here into the details, but you could effectively plug in your favorite method for approximating the Koopman operator here. The one thing that is sort of like an extra ingredient, oops, I did something. I pressed the wrong button, I think. sorry. There is an extra ingredient is that we need to have a version of implementing this quantum base rule. It will become apparent in a moment. We need some type of kernel, feature map, operator valued feature map for that. But in essence, what happens is that we have our classical system that represents the resolved degrees of freedom and a quantum system that represents the unresolved degrees of freedom. And these two are evolving in tandem in a sort of like prediction corrector cycle, similar to data assimilation, whereby at a given time step, the quantum system provides information about the closure terms as a quantum expectation, and the classical system updates the state of the quantum system using this base rule, treating the resolved state as a quantum event, as a quantum effect. And between these updates, the density evolves under the Koopman operator unitarily. And so we cycle through this process, and that gives us a closed system. I will first do a quick illustration for Lorentz 63. This is basically replicating the Palmer's example, where we take the Lorentz 63 system, we represent it into a PCA coordinate basis, so that basically these variables here capture increasingly smaller variants of the state vector. So there's like a bit funny looking representation of the Lorentz 63 equations, but it's equivalent, and we're treating the third variable, the least variance, capturing as unresolved, and we want to parameterize it using these two as the resolved equations, and left alone, these two cannot basically reproduce chaos, right? Because this is a two-dimensional smooth system in R2, but we want to recover the chaotic Lorentz attractor, and we do with, I would say, fairly decent accuracy. This is a comparison between the true and reconstructed system after this quantum mechanical closure. And also this is a comparison with the Gaussian closure from Palmer's paper. What I want to highlight here is that even though that's not a necessity for a successful closure scheme, the quantum mechanical closure actually reconstructs the full Lorentz attractor even in the third coordinate. So it kind of like there's enough information to recover the three-dimensional attractor and associated with the unresolved variables. Whereas here in this picture, this is not done because effectively the Gaussian closure scheme is representing the unresolved degrees of freedom by a coin toss at every step. So the structure in the unresolved degree of freedom is lost. And just as a comparison, we get the correlation structure and other like low order statistics well represented. So this was going to be about PDEs, and I have, I guess, remarkably, I still have 7 minutes, so I guess we'll have some time to talk about PDEs, where the extra piece of ingredient here is that the state space of our original system is itself a function space. Like take, for instance, a fluid mechanical model, and there is a spatial structure basically associated with the state that we want to take into account. Here, I will come back to that in a bit more detail. One of the structures that we want to exploit and at least take into consideration is like symmetry operations in the spatial domain, like translations and so forth. So that's the extra ingredient, but otherwise the scheme remains sort of like morally the same as before, with the difference that now we have a quantum. You can imagine having a field of quantum states when we parameterize the system, rather than having one quantum state, as in the case of an ODE. Here we're putting essentially a quantum field representation of the unresolved degrees of freedom, embedding a field of density operators that will be coupled with the classical systems, and the turbulence fluxes the closure terms that we want to capture are basically function valued functions. Like for every basically state of the unresolved degrees of freedom, we have a spatial field of closure terms that needs to be represented. So that creates some unfortunate notational complexity, but morally speaking, again, the scheme is the same as what I was showing you previously for ODE. We have to be a bit careful about the choice of Hilbert space, and if I don't mess up the button here, I will mention that we're working in a product space that includes also the spatial the spatial domain. We can think of it either as a space of function-valued functions on the state space of the PDE, or equivalently as a space of scalar-valued functions on a product domain. And what we want to do, we want to choose the subspace of that Hilbert space in which we perform our approximations to take into account dynamical symmetries. So we imagine that there is, or we allow the fact that there could be a symmetric group that is acting on the spatial domain. And by symmetry here, we mean that you can translate initial conditions by your symmetry group or translate entire solutions, and those translated solutions are again solutions for a translated initial condition. This can be formulated in terms of like a commutation or intertwining relation with a group. But these symmetries also induce, this group operation induce some flow on the Hilbert space that we have, and that we want to factor out. Essentially, we want to have an efficient representation that quotients out the symmetries. I don't have, I think, time to go into the details of that, and I'm happy to talk about it offline, but we use essentially a version of delay coordinate maps that is done on individual, think of it as space-time points, that we have basically a delay coordinate map for every spatial point in the domain. And by using that approach in combination with a kernel method, we basically can obtain a basis for our Hilbert space that is invariant or equivariant under the symmetries of the dynamical system, and that gives us a more efficient. It's important to get a more efficient representation for these high-dimensional PD systems. So I will end with one example in the next couple of minutes that I believe I have. So it will be the shallow water equation. This is like a prototypical PDE that for like governs the motion of a fluid. This is in 1D on a shallow layer, as the name suggests. It has this structure here. It's like a nonlinear PD, and it's been studied extensively, and finds applicability in many different domains. But also it has been used to study closure schemes. So here we took after like the setup from a paper of Timofeyev and co-authors from 2024, where we basically take the shallow water equations, do a spatial averaging, coarsening to get a core system that will be our resolved dynamics, and that's what we want to do a closure, to basically reproduce aspects of that PD from the core system. And one of the qualitative features that we want to recover is like the development of these sharp propagating fronts that the shallow waters equation develop. Somehow I think this ran out of battery, but the panels in the left are showing the true H variable is like a space-time diagram for the height variable of the shallow water equations, where you can see that the solutions have this sharp front, and here we have the momentum variable Q again of the true system. And the challenge here is to basically capture the behavior in this sharp fronts, where this is where all the action happens, all the turbulence, like the backscatter from the unresolved degrees of freedom feed in to create these dynamics. The quantum mechanical closure is shown here on the intermediate panels, and qualitatively it does again a good job in reproducing the original dynamic. There is some additional diffusion, as one might expect. This is actually a pretty challenging problem to reconstruct faithfully, because it develops arbitrarily small length scales over time. So basically done. I'll leave this slide on. I think there are many interesting open questions in this general area, the interface between Koopman or operator method for dynamical systems and techniques from quantum theory and quantum information science. And yeah, thank you, and I'll stop here.